So this is today, which is 7.1. And these lecture worksheets, this is the one that was referenced in the video you just saw. So this is the medal activity series, and you're going to want to use this medal activity series as a reference. So you don't need to memorize it, but you need to have it handy. Just like you need a periodic table, you need this. So this is the list of metals that you will see in reactions, like single replacement reactions. So this is going to be predicting products of what are called replacement reactions. So these are called single replacement reactions when one metal will replace another metal. And so this is called the activity series. This activity series is the listing of metals from high activity to low activity. So these are the most reactive at the top, and these are the least reactive at the bottom. And these are the metal activity series is if one metal will replace another metal in a chemical reaction that is called a single replacement reaction. So we're going to be looking at single replacement reactions and then continue on to double replacement reactions. Now you can use this activity series for either single replacement or double replacement, but it is most useful for single replacement reactions. So that's called the replacement reaction. And it is when one metal replaces another metal in single replacement. So the metals at the top are the most reactive. That's what highest activity means. And the metals at the bottom are the least reactive. That's what lowest activity means. And so what happens is that if one metal is higher than the other metal, the higher metal will replace any lower metal. Okay, and so for instance, you take two metals, any two metals on here, and you compare them. The higher one will take the spot of the lower one, and that means a replacement will happen. Okay, and so this using the activity series is just basically looking at the activity series and comparing two metals. And so you need to have the chemical symbol, the element symbol, when you're given the element name like lead or sodium, because what you have here are element symbols. You have Li instead of the name lithium, or you have K instead of the name potassium. So you might need a periodic table handy that has those names if you don't remember those names. Okay, so if you are comparing lead versus sodium, you need the element symbol for lead, which is Pb. And then you need the element symbol. You're comparing this to sodium, and sodium is the element symbol Na. So then you go back with those element symbols and you find who's higher and who's lower. So where's Pb and Na? So here's Na here, and here's Pb here. So which metal is going to be more reactive? Whoops, go back to blue. The higher metal is more reactive, so you just want to underline the more reactive. That's the higher metal. So what that means is that sodium would replace the lead in a reaction. Now we're not given any reaction yet, so we just need to decide which is the more reactive metal. Okay, so that's good for now. For the next, you have potassium or lead. Who's more reactive? So again, you need the element symbol for potassium, which is K. And then this is compared to lead, which is still Pb. So let's take a look at potassium versus lead. So that is here's potassium is K, and then the lead Pb is down there. So who's more reactive? That's the potassium. And so understanding why it's more reactive has to do with the valence electrons. It also has to do with this concept called electronegativity. But there's there's a combination of reasons why one metal is has higher activity than another. You guys just need to understand how to use this table. Okay, so let's take a look at the next one, which is copper or zinc. So copper is the element symbol Cu compared to zinc, which is the element symbol Zn. So in taking a look at this, we have Zn is here. Oops, let's erase this. Okay, so we have Zn is here and copper is here. So who's more reactive? Who's higher up is this one, the Zn. Okay. And then hydrogen or gold. So hydrogen is the element symbol H. And then you will find, you'll find that hydrogen is listed on this activity series as H2. So this is hydrogen. And why is it written as H2 instead of H? It's because this is the activity series for metals, and metals are the atomic elements. Metals are typically present just as the individual atoms. Hydrogen, though, is also on there because hydrogen can act like a metal when it is in family 1A. The hydrogen is listed in that first column and it can act like a metal. But it's written H2 on here because it is to make it clear that you will see H2, hydrogen H2 in nature, always written as H2, diatomic, not just H. Okay, so this is just H compared to gold, which is AU. Okay, so you can write H or you can write H2. What you're looking for is just hydrogen on there. Okay, so H, H2, they are equivalent. And so which is more reactive? The AU, the gold is down here, hydrogen is up there. So who's more reactive is that H2 or H if you find it. And then finally, this one is mercury or silver. So the element symbol for mercury is Hg versus silver, that is Ag. And mercury, silver, gold, those all are element symbols that do not align with the element name. Why? Because those are those precious metals that I mentioned. They can be found in nature in their just in their state as a metal alone. So you can find a chunk of gold, or you can find a chunk of silver, or a chunk of copper, as compared to, compared to up here, the more active metals, these guys, lithium, potassium, calcium, those have already reacted, and you cannot find easily a chunk of lithium or a chunk of potassium or a chunk of calcium. Now, what does that mean that they've already reacted? It means that they formed the ions. That's what metals do, is they form ions, and they form those positive charge cations. Metals form cations, and then those cations then find anions to bond with. So they react by forming ions and then ionic bonds. So those are ionic compounds. So what it means down here is that these are metals that are not reactive. They don't tend to form ions. And so therefore you can find them in their non-ion state as just elements alone. And so that's why they're called precious metals. Most metals you won't find as metals alone. You can't find these metals. You'll find them as metal ions in other things. Okay. And so because they were able to be found, these were given, they have these names that go back in time to before the standardization of periodic table element names. Okay, so back to that was a little aside. You know, I can talk about the periodic table for days and days and days. So I always try to sneak it in there. So mercury versus silver. Here's mercury and here's silver. So as long as it's above it, even by 1, it's considered the more reactive metal. So that's what the one you would underline. Okay. So you are always going to be given reactants in these types of problems that are called predicting products of replacement reactions. And so the background is that in the single replacement, you have one metal replacing another metal, and you're always going to be given those first, what are those 2 reactants? So these over here in this example are the reactants. The reactants are on the left. So you're always going to be given what those reactants are. And these are the generalized reactants A and B, C. And then on the other side, you will have to predict the products. Okay. So it's actually 2 steps. You first have to figure out if there's going to be a reaction happening. How do you do that? That is using the activity series. So when one metal, that's what this says, when one metal A is more reactive, it will replace the other metal, and that is the other metal will be replaced. And that other metal is going to be a metal that is in an ionic compound. So notice this is an ionic compound here. Bc is the compound made out of B and C. So there's a metal cation in that ionic compound. Actually, since that already says ionic compound down there, this is the ionic compound. What I'm going to do is show you the ions, which are B is always going to be a positive charge ion. And so in this example, it is a +1 charge. There's no superscript or subscript that you can pick up, or there's no superscript indicated. So you have the ionic compound that is a positive charge and a negative charge. That's what the ionic compound is, positive and negative, okay? Cation, anion. So that metal is an ion in the compound, and you're comparing it to a metal that is not an ion, okay? So this is the first step. How do you predict if a reaction will happen? If one metal is more reactive than the other metal, it'll replace it, okay? And so when that happens, that metal that is more reactive, the more reactive metal, this is the next, is the more reactive metal forms a metal cation before it reacts to form that new compound. And so you use the activity series for two reasons. We already looked at the first, but let's now go back to this and look at the second. So let's say you knew that this sodium was more reactive, and this more reactive sodium means it will replace this lead, okay? But before it does that, it first needs to form the ion, okay? And so that's the second half of this activity series. You also use this activity series to predict the ions that are formed. And so let's add that in red, is that the ions that are formed, some of them are indicated, but let's add all of them. So for instance, zinc forms this +2 ion, or chromium forms this +3 ion, or iron forms that +2 ion. And then you have, this is tin forming the +2 ion. This is lead, Pb, forming that +2 ion. Copper forms the +2 ion, and silver forms the +1 ion. First of all, why are those indicated? Because these are metals that are able to form more than one possible ion, okay? And so this is, tin could form +2 or +4, but in a single replacement reaction, tin always starts off by forming the +2 ion. Same thing about lead, Pb. Pb can form +2 or +4 ions, but when going through the single replacement reaction, it always starts off by forming a +2 ion. Okay, so that's why these that I have with the red arrows are already indicated. These are the ions that could form more than one ion. For these other ones, what about these ions? Do these form ions? Yes, they do. Why aren't they added in there? Because you use the family number from the periodic table. So this is lithium that is in family 1A. So lithium forms a +1 ion. This is potassium, which is also in family 1A, and that forms a +1 ion. So I just put the plus instead of +1 or 1+. Calcium is in family 2A, so that forms a +2 ion or 2+. And sodium is also in 1A, and that forms a + ion. Magnesium is in family 2A, that forms a +2 ion. And this aluminum is in family 3A, and that forms a +3 ion. Okay. This is cadmium. We don't actually work with, but that forms a +2. And nickel, we will see actually coming up, and that forms a +2 ion. So this, I'm going to erase the word hydrogen because it gets in my way of adding what ion does hydrogen form when it goes in the single replacement reaction. Hydrogen forms that +1 ion. And that's when hydrogen is in family 1A, it acts like and having the 1 valence electron and losing 1 electron, +1 ion. And then you have the mercury, which forms a +2 ion, and this gold, I think, oops, hold on, didn't want to write Hg. This gold, Au, forms a +3 ion. Okay, so we have, when you are using the activity series, you use it to figure out the more reactive metal, which is higher, and then you also have to use it to figure out what the ion is formed. And so you have all that filled in now. Okay, so when you have the higher metal will form a cation. You still use the activity series to predict that. Okay. And it will form the cation, the positive charge, and then form the ionic compound. So the next step is, how do you figure out what the ionic compound is? Well, you write the ions. This is what this says. The ionic compound product, you need to write the ions with the charge values as superscripts and then use the crossover rule to write the chemical formula. And so that's how you end up writing the products, which will be a new ionic compound. This will come from the ion that the metal A formed. So this A is the more reactive. It will form the ion, drawing this arrow over here. It forms the ion. You use the activity series for that. And then that ion will combine with the negative charge, and this is the negative charge C that came from this ionic compound that was in the reactants. So that's what I mean by the replacement, is that this A replaced B. So, and it replaced B not just by basically stepping in and taking its spot. It had to do this in the chemical fashion in which A became the ion, okay? And then those ions combined, okay, the ion from the reactant, and that combination is using that crossover rule to figure out what the new ionic compound chemical formula is. So the new ionic compound chemical formula, circling this AC, does not have any plus or minus signs and also should not have any superscripts. It should only have subscripts. That's what the crossover rule does. Okay. Now, one last thing to add is that you're not always going to have a replacement. And this is when the metal alone, A, so when A is the metal alone, notice here, it's by itself. When the metal alone A is less reactive than B, no replacement happens and there's no reaction, okay? And so we will see those examples. But what that means is, I kind of like to think about this zooming in on these two reactants here. I'm going to erase this so that it's not so messy looking. But zooming in on these two reactants, you have your two reactants, A and BC. Think of it like this, where A is a single person, and BC is a couple. Okay, so this is two people, they are coupled. Well, if A is more exciting, more interesting, more whatever, more money, got a better car, A will replace B in that couple, and you will have a new couple formed. Let me erase this. So have you ever seen that happen? I hope not. But it can happen. When one is got more going on, you're going to have a breakup of this couple and a new couple forms for the guy, the girl, whoever that had more going on. And that will be a new couple, which in chemistry is a new ionic compound. And you also have a new single person. Okay, so this is a new metal alone. And zooming back out here, I want to go back to this part, which is what happens when you have that new ionic compound. I also want to mention that that new element can be a metal alone, which is called a metallic deposit. And you will see that in these reactions is that a metal appears from nowhere. Okay. And, but you also have the possibility of this new metal alone being a gas like H2. And H2, hydrogen gas, H2 is hydrogen gas. You don't see a metal appearing from nowhere. What you see when you have a gas that forms like H2, it's going to be bubbles. Okay. And so this typically happens when H is the new metal alone, becomes H2 and not just H plus. Why is that? Because hydrogen is never going to be by itself. It always will find another hydrogen. And so this is H2 and that's a gas. Okay. So let's go down and predict these. When you are given two reactants, like here, you are given this Na and FeCl2. So you have a metal and you have an ionic compound. You want to compare those two metals. So the element symbols are Na versus Fe. So go back to your activity series and look at the sodium versus the iron, Na versus Fe. So here's Na and here's Fe. You can see that the sodium Na is higher. Okay, so you just need to decide who's higher. So sodium is higher, which means it's more reactive. And if it is more reactive, it will replace the iron. So let's see if that can happen. Yes, this can happen. Sodium is the metal alone. It can take over that spot of the Fe. In that process, it doesn't just slip in there. You have to write the ions with those charge values. Okay, so what are the ions for all of these, for Na, for Fe, and Cl2? Well, we need to go back to the activity series and use the activity series to figure out what the ion of sodium is. So sodium forms the Na plus ion. So you can write that one. Okay, so sodium is going to be the Na plus ion when it goes into this single replacement. But what about the ions for Fe and Cl2? Well, you don't need the activity series for that. For that, you have the chemical formula and you use the reverse of the crossover rule. So basically, you take this chemical formula, FeCl2, you write the element symbols FeCl, split them apart. So I just moved Fe apart from Cl. You put a plus and a minus, and then that subscript 2 that I'm circling in green, that subscript is a superscript that came from this iron in the first place. So it becomes a 2 up here. Okay. And that means that this was originally this Fe plus 2 ion. And then you also had it combined with the Cl minus ion. Now, the reason why you want to write those ions is because now you want to figure out the product. Remember, the product is after the replacement. Okay, so let's figure out what replacement is going on. So this sodium will come over here and take away and replace the spot that Fe was in. So this is the sodium ion will replace the Fe2 plus ion. Okay, and so I'm going to write the chemical formulas by starting with the ions next to each other. This is the new couple, the new pairing. And then using the crossover rule, you find that the plus signs cancel out and there's no numbers to cross over and down. So that's the chemical formula of the new ionic compound that's formed, NaCl. You also have Fe2 plus. Well, what happens to Fe2 plus? Because it's still there. Well, what happens to it is no longer an ion. It becomes Fe without the positive 2 charge. Okay, so in a complete balanced equation, you should have no ions. Okay, so writing the complete balanced equation, you start with the chemical formulas of the reactants, which are Na and FeCl2. So I just copied these. Okay, so I just copied these that were given to me. And then on the other side of it, so you want to have an arrow and you want to have the products on the other side. So what are the products? The products are those two chemical formulas that I just figured out. One is the NaCl and the other is the Fe. Okay, so first you write the reactants and then the products, and then you got to balance it by adding coefficients. So use coefficients. Those are whole number values that you put in front of a chemical formula and you never change any subscripts. Okay, so don't put a 2 after NaCl, put a 2 in front of NaCl. I'm going to do that in green. Put a 2 in front of NaCl so that you could have 2 of those chlorines. Okay, so that 2 is also in front of Na, so that means there's 2 sodiums. So I need to add a 2 in front of this right here. And so that will be balanced. You got 2 sodiums on both sides, you got 2 chlorines on both sides, and you have 1 iron on both sides. So that's balanced. Okay, So let's try this next one, and doing examples is our way through this. Okay, so you are given two compounds. You're given a metal alone and an ionic compound, and you want to compare those two metals. So there's a calcium in there and also an Ag, that's silver. So go back up to the activity series and compare those two metals. So where's calcium and where's silver? Well, here's calcium up here, and here's silver way down here. Okay, so calcium is more reactive. Whoops, erase that. Calcium is more reactive and it will replace the silver. When it reacts, let's grab this at the same time, it forms the +2 ion. Okay, so calcium is more reactive because it's higher up. So let's underline that one. It's more reactive. And it will replace the silver. And before it does that, though, it has to form the ion. And so the ion that calcium forms is calcium +2. So you can use the periodic table for that, or the activity series is where I got that from. So that's the ion of the calcium. How about the ions for Ag and NO3? So that you have the chemical formula of the ionic compound is what you use. So what I first need to do is see that this is nitrate. That's NO3. So you're still going to need those polyatomic ions. That's NO3. And I put that in parentheses so that when I split this ionic compound apart, I'm going to write the Ag separate from, in parentheses, NO3. Split those apart and keep the NO3 together. Why? Because that's a polyatomic ion, and polyatomic ions by definition is atoms that are bonded together and they stay stuck together. Okay, so it doesn't split apart into separate nitrogen and oxygen. Then you want to add a plus and a minus, so Ag plus and NO3 minus. Now it's important that I had put this parentheses around the NO3, because what that means is you cannot take this 3 and pick it up and it does not become a charge value. It can't leave the parentheses. So it's important to have added the parentheses. And that's fine though, because those are the charges for silver. It's always +1. And nitrate is always going to be NO3, chemical formula with a -1 charge. Okay, so but what happens is there is a replacement. Calcium ion is going to replace, it's going to take the spot of the silver and form a new ionic compound. So I'm going to rewrite this with the calcium. That's the calcium ion 2+, with the new partner, which is NO3-. So there's a new ionic compound formed. And the way to do this is write the ions next to each other and then use the crossover rule to write the chemical formula. So this is going to be Ca and then NO3 with a 2 subscript. And there should also be no plus or minus signs. Okay, so that takes care of the replacement. So what happened there was that the calcium +2 ion replaced the silver plus ion. So what happens to that silver ion? What happens to Ag plus? Well, it's by itself, and when you have an ion alone, it does not stay with the negative charge or the positive charge, that is. It becomes just the metal alone with no charge, so just Ag. Okay, so in writing the complete balanced equation, you start with the chemical formulas of the reactants, which are up here, and I'm going to write them exactly as they were. Ca plus AgNO3. So we're given those reactants, and then have your reaction arrow. On the right side of the reaction arrow, those are the products that you predicted. That's the Ca parentheses NO3 plus Ag. Okay, so you got the reactants on the left, products on the right, and now you have to balance it, so making the atoms equal on both sides. And you can make the atoms equal on both sides. You should only add coefficients, never change any subscripts. So there's 2 of the NO3 is what I can see here. So in order to get 2 of this NO3, I need to put a 2 coefficient in front of AgNO3. That also changes the number of Ag or silver. So you need to put a 2 over here in front of Ag on the right. And then there's 1 calcium on both sides, so don't need to change anything there. but now this is balanced, and this is your complete balanced equation. Let me check and see if anyone has any questions. You guys feel like you can do this? Okay. Well, good. I know Abby can do it. So let's keep going though. Like I said, the way to do this is to keep doing examples. So let's look at the next one, Mg versus HCl. So comparing two metals is Mg, and you have the H in the HCl. So go back to the activity series and compare Mg and HCl. Okay, so I've got Mg is here. And then the H, sorry, I wasn't comparing Mg and HCl, I was comparing Mg and H. So Mg is here and H is down below. So that means Mg is more reactive and it will replace the hydrogen. So when it does that, it forms the magnesium +2 ion, Mg2+. So let's take all that and bring it back here. So this is the magnesium is more reactive. And so it will replace the hydrogen. And so it can do that because magnesium is a metal alone and hydrogen is part of an ionic compound. So you're going to write the ion that magnesium forms. It's a +2 ion. Okay. And then the ions from HCl, use the chemical formula by take H, split it apart from Cl, write the element symbols, split apart, and then add a plus and a minus. And then you want to write the new pairing. So what happens is that this magnesium takes the spot of the hydrogen. And so you have a new ionic compound. So this, you want to write the ions next to each other, Mg2+ and Cl-. Using the crossover rule, you would find the new chemical formula is MgCl2. Now you still have hydrogen sitting around. It is H+ ion. And what happens when the hydrogen is by itself is it does not stay as the ion. It will become H. Well, hydrogen does not remain as individual hydrogen atoms. It will always find another hydrogen atom and form the diatomic H2. That's the example that I showed you above, is that hydrogen forms H2 gas. Okay, so let's write the complete balanced equation where you take the original reactants, just copy those, which are Mg and HCl. And then you have your reaction arrow. On the right side, you have the products that you just predicted, which are MgCl2 plus H2. So now you need to balance this using coefficients. So I can see that there's 2 chlorines. So to have 2 chlorines on this reactant side, I need to put a coefficient 2 in front of HCl. This 2 also affects the number of hydrogens, which is good because there's a subscript 2 on the product side, H2. So that balances the hydrogens and the chlorines, and the magnesiums are already balanced with the element symbols. So this is balanced and you're set there. Okay, let's take a look at the last one, which is Al and MgCl2. So comparing two metals are Al versus Mg. Okay, so go back to the activity series. Let me erase that. Okay, and I've got aluminum, which is here, and magnesium, which is here. So who's the more reactive metal is the magnesium. So this magnesium is compared to the aluminum. Magnesium is more reactive. So let's take that. So this is the magnesium is more reactive. And the magnesium being more reactive, it will replace the aluminum. Okay, well, here's what happens in this example is magnesium, you see, is in the ionic compound. It's part of MgCl2. So it's already in the ionic compound. And it wants to go over and take away whatever, but there's nothing to replace, it basically can't take anything away from the aluminum. So this is the example when you have this magnesium is more reactive, it wants to react with anything else. Well, the only thing it can react with is an anion, a negative charge. Okay, this aluminum is never going to be a negative charge. Aluminum is a metal. Metals always form positive charges. So is the magnesium going to react with the aluminum? No. Two positive charges will repel. Okay, so what does magnesium do if it's already in the ionic compound? It already has an anion and it can't find another ion to react with. It'll stay with the original ion. So magnesium stays with the chlorine ion. And so this is an example of no reaction. And this is for two reasons. It's because aluminum is less reactive than the magnesium. And also, you also could say it differently, magnesium is more reactive than aluminum. And this goes back to the people examples in that, so why doesn't aluminum come and take away the chlorine? Because aluminum is not more reactive, it can't do that. Okay, this is something that has to have more going on in order to split up this couple and form a new couple. Well, aluminum doesn't have that. Aluminum is less reactive. So that's what this says. Aluminum is less reactive. Oops, didn't mean to switch to purple, but I guess that's good. Aluminum is less reactive. It cannot go and replace the magnesium. Or the other thing is magnesium is more reactive and it can't find anything else to react with. Okay, so that is an example of no reaction. And we will see that. And what happens in no reaction is you don't see any chemical change. Just to add on to each of these is that what type of reactions these were is based on looking at the products. So here are the two products. You have NaCl and Fe. When you have a metal alone, this is called a metallic deposit. And how that looked is you see a change. When you mix two things together, you see a change, and that typically will be like a new thing that looks like it's there. It's kind of fuzzy, it's blackish, it's silverish. And that's something when you actually can see it, you're not seeing it. It is a fuzz. It is a little bit of a color change. Well, that is a change, that is a chemical change indicating there's a new product there. Okay, so this is called a metallic deposit. And this typically will take, they're not quick. And so this is the one that I showed you, which was the blue solution. This is also a metallic deposit. This is silver. It's a metal alone. And that metallic deposit in the reaction in that video starts off looking like a kind of a grayish fuzziness, but it takes a little bit of time. I think it was sped up, and then you can shake off all of this silver that is formed, and you literally form solid silver in this single replacement reaction. This is H2. Now, H2 is not a metal. H2 is hydrogen gas. And so in this example, you will see bubbles. And that's because that is a gas. It is not a color change. Most gases are not colored. You see these little bubbles that bubble out of the solution, out of the whatever you did the experiment in. And then finally, this last reaction, which you cannot write a complete balanced equation. What you would end up writing is you rewrite the reactants, and you would write nothing on the other side of the arrow, or you would write no reaction. And this is no reaction because the two reasons: either aluminum is less reactive than the magnesium, or because the magnesium is more reactive than the aluminum. You can choose which one you want to write as the reason, but it is no reaction. So you cannot write a complete balanced equation because there's nothing on the other side. There's no products. Okay, so that is a wrap up of that. So we will be reviewing this next week. You'll see this all in lab again. So remember that, you can always fall back on this worksheet and namely the metal activity series, and using the activity series to predict and also to figure out the ions. Ideally, you have written down all of those chemical formulas for the polyatomic ions. These are the examples that I started with, which are the alkali metals, but the acetate, nitrate, and ammonium, this is all in rule 1. So I'll add ammonium, but that you need the polyatomic ion chemical formulas. So ammonium is NH4+, and you need them right there, right on this page. So you can have another page next to you with the polyatomic ions, or you can have them memorized, but you need the polyatomic ion chemical formulas in conjunction with the names. And so the rules we will be using to figure out the solubility of ionic compounds. So many ionic compounds dissolve in water. That's because water can dissolve lots of things. We'll talk about water and all of its amazing abilities and properties and why we need it in Module 8. But this is one thing to think about, is water can dissolve lots of things. But why? Why do some things dissolve in water and other things not dissolve in water? Well, it goes back to this solubility rules. Okay, so the chemistry of it is that it has to be, in general, something that is soluble. And so ionic compounds that are soluble, they will dissolve in water and form aqueous solutions. And so when you have NaCl, that's table salt. So NaCl is table salt. You have a white solid that you put in water, and then you can't see that white solid anymore. And that's because what you have is the sodium ions, Na+, and those are aqueous, that's a little AQ. And you also have chloride ions that are now separated, and that's what you saw in the video. These are particles that are now separated and you can't see anymore, okay? So that is not true of all ionic compounds. Some ionic compounds are called insoluble and they don't dissolve in water. And so that's an example of you put something in water like sand and it doesn't dissolve and you still see it. It just basically falls to the bottom. And so that we will see insoluble. So insoluble compounds that are formed in a chemical reaction and they end up on as a product, they're formed from the chemical reaction or on the right side of the reaction arrow. When it is something that is new, it's a product, it's formed and it is insoluble, it's called a precipitate. So precipitate is indicated by this PPT, and this is always on the product side. Always on the product, it's always a product, it's always on the right side of the reaction arrow. Okay, and what it is it is a solid. So it is a solid formed from the reaction. And the types of reactions we'll be looking at that form solids or ionic compounds or precipitates, these are these replacement reactions that we've been focusing on. Okay, and this focuses on those other physical states that we've already gone over. When you have a metal alone, it's going to be a solid, unless you have a gas like H2 or O2, or you can have gases like CO2 and you indicate those physical states with a parentheses as a subscript. So that's what I had here. AQ means aqueous solution. Is this AQ physical state that you put as parentheses as a subscript. And so that's what you have when you have a solid, you have an S as parentheses as a subscript, or when you have a gas, that's a G as parentheses, in parentheses as a subscript. Okay, so we're going to use these solubility rules to figure out when you have an ionic compound, will it dissolve in water? Yes or no? Okay, and so you're looking at the ions in the ionic compound. And so for this, determine the solubility and add the physical state for each of these ionic compounds. So you need to look at each ion in the compound. And so that's because if one ion is soluble, the entire compound will be soluble. And so this is K, which is potassium. That is in family 1A. And so there's a rule for that for family 1A. So this is rule 1 that says alkali metal compounds, that's family 1A. So that's why it was useful if you had written that from the video. So alkali metal compounds, let me continue just focusing on that. Alkali metal compounds, so anything in with a family 1A metal, this will be soluble, okay? So this means that because this has the potassium ion, this K plus is in family 1A, this is rule 1, which says that it is soluble. So that means you could write the entire compound KBr with an AQ. Okay, so if you find out that one half of it is soluble, you don't need to bother looking at the other half. Okay, and so this you could also, showing this is another half of it. The other half of this is Br. So Br, which is bromine. That's the other half, Br minus. Well, bromine is in family 7A. That's a halogen. And halogen also has a rule. So halogens are in family 7A. Those are halides. Those are family 7A that are anions and have an IDE ending. So this is bromine, you'll find it in 7A. So that is rule 3. And rule 3 says that those halides are also soluble. So you could get to this answer being that this is an aqueous solution, either from family 1A or family 7A, but you just need half of it to be soluble for the entire thing to be soluble. Okay, so let's look at the next one, which is LiNO3. Okay, so you have lithium ion is half of it, and the other half of it is the nitrate ion. So is there a rule for the lithium ion? And I'm going to go back up here and see that there is a rule for the lithium ion because lithium is an alkali metal. It is in family 1A. Okay, so going to here, you need the periodic table to remember sometimes what is in family 1A. So that's lithium. The lithium ion is in family 1A. That is in rule 1, it says it's soluble. So that means you could write Li and then NO3 with an AQ physical state. Okay, the other thing is that this also has the nitrate in it. So NO3 minus is a nitrate, and that is also part of rule 1, saying it's soluble. So either way, you are in rule 1, this is nitrate, and nitrates are soluble. But this will be aqueous, whether you're looking at the positive ion, the lithium, or the nitrate. This is the next one is Mg and SO4. So you have the magnesium ion, which is +2, and you have SO4 2-, and that's sulfate. Okay, so that's the sulfate ion. And Mg +2 is in family 2A. So first of all, is there a rule for family 2A for the magnesium ion? And so I don't see anything that has a rule for family 2A, okay? But you do have a rule for sulfates. This is rule 4 that says most sulfates are soluble. So remember sulfate, you want to have this, which is SO4 2-. Sulfates are soluble. Exceptions though. So these are exceptions if you have the barium, strontium, silver, lead, or calcium ion. So you got to pay attention to those exceptions. So for this one, you have sulfate, which is rule 4, which says this is soluble as long as it's not one of those exceptions. So you check, is magnesium one of those exceptions? And the answer is no. So that means it's still soluble, so that you would write MgSO4 with an AQ physical state. Okay, and there's nothing for the magnesium. There's no rule for family 2A. Okay, so next let's take a look at the Ag and I. So this is Ag, this is Ag plus, that's silver. And then there's I minus, and this is iodide, which is in family 7A. Okay, so there's no rule for silver up here. You won't find anything about a silver in there, but you will find a rule for family 7A. Those are the halides. So this is halides, rule 3, halides, which include chlorides. So that's chlorine, bromine, iodine, fluorine. And that is where I found the iodide is in family 7A and forms the I- ion. So these are soluble except for those containing Ag, okay? Ag, Pb plus 2, and that's the mercury ion. So this is a family 7A, but it is an exception. And it's an exception because it has the silver ion. So see that silver ion that's there? Well, it's not soluble. So that means it's not soluble. So insoluble means that you write that this is going to be AgI, chemical formula, moving this up, and it is going to be your precipitate. So those are insoluble. Those are solids that are formed on the product side. Okay, so PPT, that's called a precipitate, remember. And then when you have AlPO4, this is the last one. So you have aluminum ion, Al plus 3, and then PO4 3 minus. This is aluminum ion or family 3A. You won't find any rule for family 3A or for aluminum, but you will find a rule for this one. This is the polyatomic ion called phosphate. That's rule 5, which says that most phosphates, carbonates, chromates, and sulfides are insoluble. And let's look at the exceptions. The exception is if you have an alkali metal, that's anything in family 1A is the cation, or if you have ammonium, and that's ammonium, that's NH4 plus. So you have phosphate, yes, but you have aluminum bonded to it. So that means that this is, phosphates are rule 5. And rule 5 says that these are insoluble. And it's not one of those exceptions. So it's not an alkali metal or ammonium because it's aluminum that's stuck to the phosphate. So it's insoluble, which means that this is not dissolved. It's not aqueous. So you'd write AlPO4, and this would be a PPT, precipitate. Okay, so that's what not soluble means. And so this is, we have double replacement reactions. So double replacement reactions are interesting because when we had single replacement reactions, remember you had the ionic compound that got broken up by the single person that comes in. Well, this time using people examples, you got 2 couples. And if you've ever seen this where 2 couples break up and then they have 2 new couples, but everyone switched partners. Okay, so that is what goes on in general. But what you do for the double replacement reaction is you write the ions with new partners, and then you use the crossover rule to write the new ionic compounds. Now, the one thing that's different about this, there's a couple different things, is you don't need to use the activity series. That's because one metal will always be more reactive and you're always going to have replacement. Okay, so you will always have replacement, but the one thing that is different, so let me write that down. You always will have replacement. You'll always have these ions switching places, okay? But what you will not always have is a product. And so we're going to get to that. Your products always have to have a gas, water, or a precipitate. Now, precipitate is the most common, and this is, you figure out precipitate using those solubility rules. That's what we started with, okay? But you have to look at the products. And if you have no gas, water, or precipitate, then that will be an example of no reaction. So you will not always have permanent products. And those permanent products are the gas, water, or a precipitate, PPT. Okay, so that's what permanent products mean. If both of the products are aqueous or AQ physical state, then that will be an example of no reaction. Even though you can get the ions to switch places, they have to have something permanent on the other side. And aqueous is not permanent. Okay, so let's take a look at these examples. This is KCl, which is, there are two reactants, KCl and AgNO3. So you want to start by writing the ions with those charge values. How do you do that with the chemical formulas? Same as before, you write the element symbols by splitting them apart. So you write K separate from Cl, and then you add a plus and a minus. So that cation, the plus charge is always first. The other one is AgNO3. Before splitting this apart, you recognize that NO3 is a polyatomic. So put that in parentheses. And then when you split this apart, it's Ag plus, and then in parentheses, NO3 minus. Okay, so you add a plus and a minus. And now you make sure that everybody switches places. So how do you do this? You write this ion K plus with a new partner. Instead of Cl minus, you write the NO3 minus next to it. So not just any partner, that this is a positive charge, which needs a new negative charge. Okay. Now the next thing I'm going to write is the other positive charge. Why am I going to write the other positive charge, the Ag plus, instead of Cl minus? Because the positive charge is always first in a chemical formula. So Ag plus needs a new partner. And so this Ag plus will look for another new partner that's negative charge, and that's going to be Cl minus. So it's not like it's actually going backwards or anything. It's just that each positive charge needs a negative charge, and the positive charge is written first. So using the crossover rule to write the chemical formulas, you cross any numbers over and down and get rid of the positive and negative signs. This would be KNO3, and the other one is going to be AgCl. Okay, so writing the complete balanced equation, you start with copying the exact chemical formulas from that you were given. So those are the reactants. So that's KCl, AQ, plus AgNO3, AQ. And then you have an arrow. So those are your reactants. On the other side, you've got your products, which are KNO3, AQ, and AgCl. Oh, sorry. You have your products, but you don't know those physical states yet. So I'm just going to write KNO3 and AgCl. Okay, so you have to use the solubility rules to figure out those physical states. So the solubility rules of KNO3 and AgCl, these. So I'm going to do this. So you have K plus and NO3 minus. I apologize in advance for going over. If you have to go, just go, and you can watch the rest of this as the recording later. But if you can, stay. So this is K plus, which is in family 1A. That is family 1A. Those are soluble. So this is also NO3 minus. That's nitrate, and nitrates are, both of these are rule 1, which say that they're soluble. Okay, so I can add the physical state AQ after the KNO3. But for AgCl, this is Ag plus and Cl minus. There's no rule for silver, but there is a rule for chloride. That's in family 7A. That's rule 3. And it says that rule 3, okay, actually, I'm going to go back to this. This is anything in rule 3. Those are the halides. We looked at these that have silver. So halides that have silver, so that's chlorine with silver, is not soluble, because this is a halide is soluble except those that have silver. So we saw that example before. So that is going to be not soluble. And so not soluble means PPT. So that's not soluble. It's one of those exceptions. So that means it's a PPT. Okay. So for the complete balanced equation, you have the reactants, you have the products that you figured out from writing the chemical formulas and using the crossover rule. You also have to have the physical states, and then you balance it. So in balancing this, you're making sure that every atom is equal on both sides. And so I don't need any coefficients. You have equal amounts of atoms on both sides. Okay, so let's take a look at the next one, which is HBr, AQ, and LiOH. So you want to start by writing those reactant ions by splitting this apart. Whoops, I'm writing this HBr first. So H plus and Br minus. So split them apart, put a plus and a minus. And before you split apart LiOH, put a parentheses around OH. It doesn't split apart into separate oxygen and hydrogen. And that you recognize is the hydroxide ion. Okay, so then make sure everybody has new partners when you're writing the products. So write the hydrogen positive ion with a new negative ion. So that would be with OH minus. And then write the lithium positive ion with a new negative partner, and that would be Br minus. Using the crossover rule, you're crossing any numbers over and down and getting rid of the plus and minus signs. So with HOH, this actually is the one of those rare times that you can break into the parentheses, and that's actually written as H2O, which is, you might recognize, water. And this water has the physical state of L. Even though there are many liquids, those liquids are usually aqueous solutions. There's something dissolved in it. Water gets a special designation. It is the L physical state liquid because there's nothing dissolved in it. And then you have LIBR. So LIBR has no numbers to cross over and down, so you just get rid of the plus and minus signs. So LIBR, we need the physical state of that. And so lithium ion is in family 1A. And for family 1A, those are this is rule 1. Family 1A has rule 1, and those are all soluble. So you can add an AQ. So writing the complete balanced equation here, you start with the copy exactly those reactants, which are HBr, AQ, and LiOH, AQ. And then have an arrow, and you have those products that you just predicted, which are H2O, liquid, and LIBR, AQ. So one little thing is that you will find that this H2O is kind of tricky to balance. And what I like to do in order to balance it is I rewrite over it. I write over it the HOH that it originated as. And that will help you see that you have one hydrogen and one hydroxide instead of two hydrogens, okay? So you have one hydrogen and one hydroxide in H2O. So you actually don't need to add any coefficients. This is balanced. You have one of everything in there. Okay, so that's balanced. And then this next example is Na2CO3, writing those ions. This I will recognize as CO3. So when I split this apart, it's Na plus and CO3 minus. So what this subscript is actually going to get picked up. So there's a 2 here that gets picked up and pulled over, not to this check mark, but it becomes a 2 on that CO3 minus 2. And that is the carbonate ion. You should recognize that one. For this other CONO3, this is CO 2 plus, and in parentheses, you already have the NO3 minus. So when I split this apart, I picked up that 2. So when you have the products, you want to rewrite this with the new partners. So it's Na plus and NO3 minus. And then you also have CO2 plus and CO3 2 minus. So then using the crossover rule, you're going to end up with NaNO3, no plus or minus signs, and you can get rid of the parentheses. And also this is going to be CO and then CO3, where you can get rid of the plus and minus signs and also the 2s. Okay. And so looking at the solubility rules, you have Na, which is in family 1A. That's rule 1. Family 1A is soluble. So that's going to be aqueous. So you don't need to bother with the NO3, but that's also rule 1. CO3. This is CO3, which is a carbonate ion. And carbonate ions, going back up here, are rule 5. This is carbonate. So CO3 2 minus is carbonate. And that rule 5 says that these phosphates, carbonates, chromates, sulfides are insoluble. Let me erase this. And insoluble means that it is going to be a precipitate. So insoluble, remember, means precipitate. So let's bring this back down here. And so this, when you are having this, is going to be the physical state PPT compared to the NaNO3 AQ. Okay, soluble is AQ. So writing the complete balanced equation, you take the reactants just as they were given. So rewrite Na2CO3AQ and CONO3-2AQ. So you were given those physical states. And then on the product side, you have NaNO3AQ and COCO3PPT. To balance this, it looks like I'm going to need to add a coefficient because there's 2 of those NO3s. And so I'm going to put a 2 in front of NaNO3. So there's going to be 2 of those. This 2 coefficient also affects the Na, the sodium, and that's also the 2 sodiums on that side. Everything else balances out. There's 1 of those and 1 of those, 1 carbonate and 1 cobalt. Okay, and then finally, let's take a look at this one, HCl and BaOH2. This is writing those ions, H plus and Cl minus, and then Ba2 plus and OH minus. So this 2 is a subscript outside of the parentheses. It gets picked up and becomes the +2 charge on the barium. So writing the new partners is going to be H plus and OH minus. And then also Ba2 plus with the new partner Cl minus. Using the crossover rule, remember when you have H plus and OH minus, this becomes H and OH, no plus or minus signs. But you would write that, this is the one of those rare times you get to break into the parentheses of the polyatomic. This actually is written as H2O, okay, with the physical state L. And the other is BaCl and 2. This 2 crosses over and down and you have no plus or minus signs. So the physical state of BaCl is you need the barium is in family 2A, and you don't have any rules for family 2A, but chlorine is in family 7A. And this family 7A, those are those halides. I'll show you back up here. Family 7A are those halides. That's rule 3. And it says that halides are soluble. So halides are soluble, including the chlorine. And let's read this. They're soluble with these exceptions, Ag, Pb, or Hg. Okay, so this is the chlorine. And what it has stuck to it is a barium. So it's not one of those exceptions, meaning that it is soluble. Okay, the other one we looked at, which was the silver with the chlorine, that was an exception. So that was insoluble, but this is soluble. So that gets a PPT, physical state. And so the complete balanced equation, you want to take those reactants and copy them exactly. This is HCl, AQ, and BaOH2, AQ. And then have your arrow. On the other side of the arrow, you're going to write the H2O, liquid, and then the BaCl2, PPT. Okay. And so when you have the H2O, it helps to write above it. Okay, even though you want to write H2O, above it, you want to remind yourself that it came from a hydrogen and a hydroxide. So that it's not that there's 2 H's, but there's 1 hydrogen and then there's 1 hydrogen that's in the OH. So that will help because you can see that there's 2 OHs here, which means I'm going to need to actually put a 2 in front of H2O because I need 2 hydroxides. See that, 2 OHs? So when I add that 2 in front of the H2O, which is really 2 HOHs, it will also indicate that I need 2 H's, 2 hydrogens. So I'm going to put a 2 in front of HCl. So that will give me 2 hydrogens. It'll also give me 2 chlorines, which is in that BaCl2. That subscript means that there's already 2 chlorines. And then there's also 1 barium on both sides, so don't need to fix that. So this is now balanced with those coefficients. Okay, this is why is BaCl2 a precipitate? Because going back up to rule 3, which is that you have chlorides. So chloride is in family 7A, that's the chlorine. And these are soluble, except for those containing, oh, sorry, it's not. You're right about that. So that's that is soluble, and barium is not an exception. Sorry about that. So this is not a precipitate. This gets to be an AQ. I wrote soluble, didn't I? Okay, so that is going to be AQ. Thank you, Parto. So it's not a product. It is a product, but it is aqueous. It is not the precipitate. Okay, I think I got that. All right, thank you. Did I get any? So let's make sure I got that, which is this BaCl2 is aqueous, not a precipitate. Was going a little too fast. And this would be the balanced chemical equation there. Okay. Now, do I have any questions?